This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of future MCAT videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll be going over electron configuration, and for part 1, we're just going to talk about the parts of the electron configuration and then quantum numbers. We won't get into actually making the electron configurations until part 2. Energy levels are the first thing that we're going to talk about, and they are the highest order level of organization in the electron configurations. So everything else in electron configurations will fall under energy levels and be contained within energy levels. And what an energy level is a sphere around the nucleus of an atom that contains electrons. So each one of these circles that we have drawn is an energy level. And as you get further away from the nucleus, then the electrons within that energy level are considered higher energy electrons. So the electrons on the closest energy level are the lowest energy electrons. And we number these by starting with 1 on the energy level that's closest to the atom. And then as we get further away, we just add 1 number. And the numbers can just keep going. Usually you're going to see it stop with about 7. That's about the highest energy level that you're really going to see on the MCAT. The last really important thing about energy levels is the idea of subshells. So we're going to go over subshells here really soon. But what you need to know right now is that as you go up in energy levels, those energy levels contain more subshells. So starting with energy level 1 contains only the S subshell. Energy level 2 contains the S and the P subshell. And then notice how every time we go up in energy level, we add 1 subshell. But that doesn't continue for energy levels 4 to 5. We don't keep adding subshells. The reason that is simply because whenever we get to actually filling in electron configurations, you're not ever going to have enough electrons to need more than the 5F subshell. So there would be more subshells if we had more electrons, but that's never going to happen, so we don't even need to talk about more subshells than just the F1. So now let's go over exactly what subshells are. Subshells are areas of space within an energy level that the electrons actually exist. So remember we said energy levels contain subshells, and then the subshell is just a more descriptive way of describing where the electron actually is in the energy level. You want to be really clear on this idea that a subshell, like subshell S for instance, has an associated number. So I can say subshell S or subshell 0 whenever, and then just memorize the associated number for each of these. If you just remember the order of subshells, the associated number is easy because it just goes up by 1. So S is first, P is next, P would be number 1, and then so on, D would be 2, and F would be 3. The next thing you want to make sure you have memorized really well is how many orbitals are within a subshell. And an orbital is an even more specific way of describing where the electrons actually reside. So the subshell tells us the general space within an energy level, and then an orbital is just even more specific than that. And the number of orbitals within the subshells, we start with 1 for S, and then we just add 2 every time that we increase our subshell. So subshell P has 3 orbitals, and then just add 2 to get to 5 for D, and then F has 7. And each orbital can contain 2 electrons. So for the S subshell, we can have a total of 2 electrons. For the P subshell, we have 3 orbitals, so that would be a total of 6 electrons. D has 5 orbitals, so 10 electrons, and then 14 electrons for F. So just to summarize our organizational structure of electron configurations, our first level of organization was the energy level. And then energy levels contained subshells, and then subshells contained orbitals. And then the electrons were contained within the orbitals. So the orbitals are where the electrons actually lie. Let's break down the organization of one of these energy levels as an example, just like we have done here. So let's just do energy level 3, for example. So write the energy level first, and then we'll write down what subshells are contained within the energy level. So for energy level 3, that would be the S subshell, the P subshell, and the D subshell. And then let's look at how many orbitals are contained within each subshell. So for S, that's just 1. P has 3 orbitals, and then D has 5 orbitals. And then we'll just make a number for the amount of electrons that can be contained within the total subshell. So for S, it only has 1 orbital. Each orbital contains 2 electrons, so that would just be 2 electrons total for the S subshell. The P subshell contains 3 orbitals, each one holds 2, so that would be a total of 6 electrons. And then finally, the D subshell has 5 orbitals, to each would be 10 electrons. So then we could just say total, the third energy level can hold 18 electrons. And the way we just broke that down isn't anything you have to necessarily practice. It's just a good way to kind of illustrate the organization of electron configurations. The last thing we'll go over are quantum numbers. And quantum numbers are just a way to numerically describe each of the levels of organization that we've talked about so far. So the energy level, the subshell, and the orbital can all be described with just a number, and these are called the quantum numbers. And this is something that's not nearly as high yield as the rest of electron configuration, but if you can accurately describe an electron based off of its quantum numbers, then you will be very well prepared for any electron configuration question on the test. So this, combined with actually filling in the electron configurations, which we'll go over in part 2, are a great way to test yourself and make sure you're totally good on this topic. The energy level was the first level of organization that we talked about, and the quantum number for that is called the principal quantum number. And the principal quantum number is represented by the letter N. And then, as we discussed early in the video again, N is just going to be whole numbers. So starting at the lowest energy level or the lowest principal quantum number, that's going to be 1, and then we just add 1 as we go up energy levels, and that can just continue on. And that's probably going to top out at about 7. You're usually never going to see many problems that have electrons that are in an energy level past 7. The next level of organization that we went over was the subshell, and the quantum number for that is called the azimuthal quantum number. And this first table is something you want to be really comfortable with, and this is the number that's associated with each subshell. So S is associated with 0 every time. P is 1, D is 2, and F is 3. So we would say that the associated number, those are the azimuthal quantum numbers associated with the subshell. And then you want to be thinking about your energy levels and what azimuthal numbers they contain. So just for example, let's just look at number 3. Energy level 3 has the S, P, and D subshells, so then it contains the 0, 1, and 2 azimuthal numbers. And you might be familiar seeing this equation 0 to n minus 1 to describe your azimuthal number. So a lot of textbooks will have L equals 0 to n minus 1. And what that is saying is that the possible azimuthal numbers within an energy level would be 0 to n minus 1. So if we look at principal quantum number 1, then the possible azimuthal numbers would be 0 to n minus 1. And then if you plug in the principal quantum number, which is n, if you plug that in for n in the equation, then our possible azimuthal numbers become 0 to n minus 1, so that's 1 minus 1. So then it is 0 to 0. So your possible azimuthal numbers are only 0. And I'll just do this for one more so you can see it for energy level 3. So the possible azimuthal numbers would be 0 to n minus 1, and then for energy level 3, n is 3. So we go 0 to 3 minus 1, which that is going to equal 0 to 2. And then sure enough, if you look at your azimuthal numbers, we do contain 0, 1, and 2 because it has the S, P, and D subshells. So sometimes you might be given a question like, if we have principal quantum number 5, what possible azimuthal numbers could an electron have that's in energy level 5, or that's in principal quantum number 5? And then you'd have to use that equation 0 to n minus 1. So then the possible azimuthal numbers could be 0 to 4. Now on this chart, if you notice, we don't go past 3. And again, that is just because, just like one of the reasons we had earlier, you're just never going to have enough electrons to go past the 4th subshell. So you're never going to have higher than a number 3 azimuthal number, even though it's theoretically possible that you could if you had enough electrons. The last level of organization we'll go over is the magnetic number, which is used to represent orbitals. So orbitals, quantum number is called the magnetic number. And you may have seen this equation in textbooks, but the magnetic number can range from negative L to positive L. So negative L to positive L. And remember that L is the azimuthal number. So let's just go through each possible azimuthal number and look at how this equation, negative L to positive L, makes sense. So first S, think about what is the number for S. That is 0. So negative 0 to 0 is just 0. So the possible magnetic numbers is just 0. Now if we look at P, P's azimuthal number would be 1. So then negative 1 to positive 1 are the possible magnetic numbers that an electron within the P subshell could have. So that would be negative 1, 0, and positive 1. So if you notice, each of our lines is an orbital, and then it gets labeled with a number. So the numbers are basically just describing what orbital we are in. And then let's just look at D, and then F will just follow the same pattern that the rest of these have. So D has an azimuthal number of 2, so that would range from negative 2 to positive 2. So then just label your 5 lines, because each line is an orbital. Negative 2, negative 1, 0, plus 1, positive 2. So your equation negative L to positive L, if you plug in the azimuthal number into L and then write down each whole number between those two numbers of negative L to positive L, the amount of numbers you have should always be equal to the number of orbitals that you have in that subshell. There's a wide variety of questions they could ask you about these magnetic numbers, but let's just do a quick example to give you some practice on really thinking about how to work through these. So a harder type of question they could ask would be, if you're given energy level 3, so N equals 3, they could ask something like, which one of these is not a possible magnetic number for energy level 3? So let's just do an example where we say, in energy level 3, can you have a magnetic number equal positive 3? And the way you'd want to think about this is just first look at energy level 3, and then think about what subshells do I have in energy level 3, and that would be S, P, and D. So energy level 3 can have the following azimuthal quantum numbers. It can have 0, it can have 1, and then it can have 2. So those are the possible azimuthal numbers. And now we want to think about what are the possible magnetic numbers within each subshell. So remember, this is negative L to positive L. So L is the azimuthal number. So for 0, negative 0 to positive 0, that would just be 0. For 1, we have negative 1, we have 0, and then we have positive 1. And then for D, for the D subshell, or for L equals 2, we have negative 2, we have negative 1, 0, positive 1, and then positive 2. So nowhere in there do we see positive 3 show up for the magnetic number. So then this answer would be no, it's not possible to have a magnetic number of 3 in the third energy level.